Once our field season's over, we have to pack up and get all of our samples back to the US.
In the field is where you get the big ideas, but you really have to wait to get back to the lab until you can confirm any of that through the nitty-gritty of the data analysis.
So after a successful expedition, we come back with our ice cores, our volcanic ash, and our surface class for cosmogenic nuclide dating.
Once we get our samples back here at Boston University, we do a variety of things with them. A lot of analyses on any sort of sediment samples to get an idea of grain sizes. We can also look at the chemistry of the samples.
And this provides our radiometric control to show that the ice is older than 4 million years or 5 million years. The ancient ice is so important because it's an incredible archive for climate.
It's not the ice itself, it's little tiny air bubbles that get frozen into that ice, because those air bubbles actually are atmosphere from the time when that ice was laid down. So instead of trying to think of a proxy for understanding what the carbon dioxide levels were or even the temperatures, we can actually find a sample of the atmosphere and do geochemical tests to reconstruct what the temperatures were, and we can measure the gas concentrations to find out CO2 levels.
So far, the oldest ice we've been able to date has been about 8 million years old.
We think if we can push that record back another couple of million years, we can answer some really big questions. And one of those questions is what happens with significantly higher carbon dioxide levels. And we have good indicators to say that we had those carbon dioxide levels in the Pliocene. So now one of our big goals is to be able to get actual atmosphere from those time periods.
As our engineering technology improves, we think we can access ice that may be up to 13 to 14 million years old. One of the great values of understanding atmospheric evolution over long timescales is it'll allow us to understand why the Earth was warmer in the past, and also, at the same time, since we're in Antarctica, understand what happened to the ice sheet during those past episodes of warmth and cooling. And so, when we go to Antarctica, we not only collect samples of ancient atmosphere, we also collect evidence for past variations in the size of the Antarctic ice sheets. And when we combine those together, it's very powerful in terms of predicting the future behavior of these ice sheets with increased atmospheric CO2.